Hey guys, welcome to Need It Make It. I'm Mike. So the challenge today is to find a way to securely connect big 3D printed parts together without having to worry about the fit, no sanding, no filing, no nothing. Just print and assemble. So if you're curious, stick around to find out what on earth I'm talking about. Printers are faster, they're also getting bigger, and that means that we can print things we wouldn't dare print before. Here's an example of something you might see printed these days. It could be a frame or maybe an enclosure. Even though we have bigger printers, they're not normally big enough and we need to split those parts into pieces. Some slicers have a pretty cool feature already to add sliding dovetails to connect the parts together, and it's not a bad idea at all, but there are some issues with that. For one, if the parts are large and if the connection isn't perfect, it's going to be either too loose or make more work for you to have to sand or file the parts to fit. The other issue is that the parts don't come into the slicer with the cuts already, which means they're not repeatable, or at least it's very hard to duplicate the cuts. If you update the file, for example, it's going to be incredibly difficult to reproduce those cuts exactly. The connection I want to try out today is hundreds, if not thousands of years old, and it is known as a scarf joint. It's actually a little more than just a scarf. It's called an undersquinted stop splayed scarf joint. And it's a very strong connection, and its main purpose is for connecting long timbers together for traditional timber frame home building. I'd like to have something to compare against, and for that, we're going to do these two samples with more typical connections. The first connection is a bolted joint with a half lap. I have 3 bolts going through into heat set brass inserts. The bolts are only 3 millimeters in diameter. It's pretty simple, easy to print, and easy to design. The second connection is created to mimic the joints we can see in the slicers. It has a sliding dovetail set at an angle to the parts, and of course the dovetail comes right through and is going to be visible through the front. This one took a little bit longer to design, but isn't that hard either. And as far as printing this, it's going to need support on occasion depending on the orientation of the parts for the interior of the dovetail itself, because we need a really good fit and supports may mess that up a little bit. So to help with that, I did add some tolerance in the dovetail to make sure that it isn't too tight. And one other note about all of these joints is that it's better to move the seam away from the connection. The seam tends to bulge just a little bit, and it may end up giving us some trouble putting those parts together. For the last, and I think most impressive connection, we need a little bit more overlap on the parts to start with. And since I'm chamfering the bottom, I'm going to set the sketch plane to 45 degrees to the edge. And now we can begin by creating a line with a pretty subtle angle of only 12.5 degrees. The angle itself isn't that important, it just should be fairly gradual. Next, we can create 2 parallel lines, and they should come back at a fairly dramatic angle. These are going to act kind of like a lock for the joint. Initially, I set these to 5 millimeters away from the top and from the bottom, but I'm going to end up changing these to 6.5 millimeters. Now we can offset the center line by 2 millimeters to each side. And then in the center, we need to create a rectangle of at least 9 millimeters wide. I'll add 2 vertical lines to remove the very sharp points on the top and bottom. And now we can cut the shape into each of the ends. And since we're 3D printing, we can fill at the corners, making the joints even stronger. And one other advantage is that the extrusion around the curve tends to be a little bit more consistent than it would be on a sharp corner. This connection could slide side to side, so I added these elongated cone shapes to keep the position centered while also allowing the connection to be assembled. Between these parts, we can extrude a rectangular piece with a split and some tolerance between the split, and I'll show you a little bit more about this connection when we go ahead to put it together. For the print settings on all of the parts, I added a little bit more cooling to the auxiliary fan to make sure we have good overhangs. So let's go ahead and get these parts printed, and I am going to be printing from Prusament PET G, which I found in previous tests to be very consistent. And I've got 2 different colors for this video just to make it a little bit more pronounced when we go ahead to put those joints together. All right, so all that's left to do is to assemble our prototype joint. So here are the wedges. Joint goes together, we just make sure it's lined up pretty close. It's more or less self-centering, so it's not really that big of a deal, but just feeling the size to make sure that they're flush. Insert one wedge in, and then insert the other wedge. And if you want a really tight joint, we just get something to push them in a little bit further. Now if we want to take this apart, it's pretty straightforward as well. We just do the opposite. These are just a little bit too big, so let's push them back out. That's it. Now just a little note about these wedges. These are cut at a 2-degree angle, and that's all that we need in order to get these wedges to work properly. The 2-degree angle will do a great job to make sure that these don't back out. So we have all 3 of our samples done and they're assembled, and I thought it'd be fun to test them out to see how each of them compare. Now if we're building a frame of some kind, it's far less likely for it to fall apart if it's assembled, but I think it's still good to know how they stack up against each other. We'll load them up with some weights and see how they hold the weight and see how they fail. Well, I didn't plan out the support of how I was going to clamp this to the table well enough, so I have this wood piece as a spacer and a pretty heavy-duty clamp. And I have this lined up where the joint comes down at the end of the joint. So when I put some pressure on this joint, it opens up here. It's quite strong, so we'll have to see how much load this one can support. I was thinking about doing a test originally like this, but I wonder whether I should rotate this. I'm going to think about that a little bit. Here's our dovetail, sliding dovetail connection. So a little bit of force and we have a fair amount of movement. Actually, it's opening up quite a bit more here than I expected. And unfortunately, when you go to try and put this joint together, you need a little bit of tolerance in order to get the joint assembled in the first place. Now, I suppose you could use a hammer and try and whack the joint together. That's a possibility. I think maybe a better option for the sliding dovetail would be to have a tapered dovetail. The further you go in, the tighter the joint gets. And even better than that would be to have a sliding dovetail going into both pieces. And that means the dovetail itself will be printed separately. And if you can do that, that means that you can spend a bit more time fine-tuning that little piece and getting the fit just perfect. So here we have the scarf joint. If we put a bit of pressure on it, not much is happening. For the most part, it's staying pretty stable, not much is opening up. I see a little bit of movement in here. As far as ways to improve this joint, that elongated shape that I made, which is kind of like a cone shape, I think that could be better integrated into the design so that it extends a little bit further to each side, is a little bit more gradual. But maybe the whole shape could change. I actually think that this 12.5-degree angle could be a little bit more slight. It could be changed to maybe 9 degrees, something like that. And it would bring this section down further and this section up a little bit further and should help to reinforce the joint a little bit better. Let's go ahead and get some testing done on these parts. But before we do, make sure you hit that subscribe button and that notification bell as well so you always know when a new video is released. All right, so the first connection we're going to test is the bolted connection with the half lap. And I'm going to load this up with 2.5 pound weights at a time because I don't think these joints can take too much load, but maybe we'll be surprised. 2.5 pounds, no problem. 5 pounds, no problem. 7.5 pounds, quite a bit of flex, but no problem. 10 pounds, oh, it's starting to part quite a bit over here. This is 12.5 pounds. Again, quite a bit of flex. 15 pounds, still good. 17.5 pounds. This is 20 pounds. 22.5 pounds. 25 pounds. 27.5 pounds. Sliding dovetail connection, we have 2.5 pounds. No problem, the joint is opening up just a little bit at the top. 5 pounds. 7.5 pounds. 10 pounds. 12.5 pounds. 15 pounds. 17.5 pounds. 20 pounds. 22.5 pounds. 25 pounds. 27.5 pounds. 30 pounds. All right, last test, we have the under squinted stop splayed scarf joint. 2.5 pounds, 5 pounds, 7.5 pounds, 10 pounds, 12.5 pounds, 15 pounds, 17.5 pounds. 20 pounds, 22.5 pounds. Quite a bit more movement up here now. 25 pounds, 27.5 pounds, 30 pounds, 32.5 pounds, 35 pounds. If I can get this on. I had to extend the cable, so 37.5 pounds. Ooh, this is heavy. 40 pounds. Opened up a lot up at the top, but it is still holding on. 42.5 pounds. This is gonna break. It's gotta break. Holy cow. This is 45 pounds. £47.5. It's gotta break. It's not breaking. All right, so I switched both cameras to slow motion. Hopefully when we actually do break this joint, we can get a good idea of what's happening. This is 50 pounds. How on earth? So correction, the last one was 52.5. I forgot to remove a plate, so this one is 55. Whoa. Whoa. So that is an extremely interesting way that it fractured. You can see that it has nothing to do with the layer lines. The wedges are just barely in there, but it did pop out at the end. It's interesting that it didn't actually break at the joint though. It broke pretty much right at the corner. So that was 55 pounds. We made it to 52.5 pounds for this connection. 25 pounds. I thought this was kind of neat. We have all three samples being tested at 25 pounds, and the amount of flex that we're seeing in the half lap joint is quite a bit more than we're seeing in the scarf joint. All right, so let's take a look at the samples and see how they turned out. So none of the samples broke on the layer lines, and you can see inside. This particular sample, if I were to redesign this one, I would have put a much larger swooping curve into here. This one was at a bit of a disadvantage. The smallest cross section was lined up right over top of the tabletop edge, and it'll focus that force, and unfortunately it broke. But none of these joints actually perform poorly, and of course the connection itself is still together. This could be redesigned to perform far better. As far as the dovetail connection goes, again, it performed fairly well. This one had an advantage over the other one in that it has a large cross section that hung over top of the table, so the tabletop edge was somewhere around here. And all of this was one piece. And you can see again, nothing broke on the layer lines. Even across this area here, it looks like it's coming across the layer lines, but it's very jagged. So I think a joint like this needs to be glued. That's probably the intent behind these. Unless you were to switch it up and change this to a sliding dovetail that goes into both pieces like I spoke about earlier. And if that sliding dovetail can also be tapered, the further that you put the dovetail piece into it, the tighter the joint becomes, and it should do a better job of holding everything together. This one was a little bit loose, although it didn't seem loose as I was putting it together, but as I was applying load, it seemed a little bit too loose. And that was with a 0.1 millimeter gap. So this one performed really well. A little bit surprised that it both fractured along here and broke here, what seemed to be at the same time. And unfortunately the video wasn't really good enough to capture it. It just was a little bit too fast for my cameras. I'd really need proper slow motion cameras. But anyways, this particular joint has some promise. I think it actually performed pretty well, and I think I could even do better with this one, like I mentioned earlier, by adjusting some of the angles and probably adjusting some of the curves in there as well. So not bad at all for a first attempt at it, but I'm interested to hear from you guys and what you think and what improvements you might make to this connection and all of the other connections as well. I'm not sure how useful this is to you, but I thought it'd be pretty cool to be able to adapt a joint used for timber framing to 3D printing, and maybe you have some ideas of your own on how to improve it or different ideas altogether. And if there is enough interest in these joints, let me know and I'd be happy to improve my test setup and test more samples as well. I'd also like to know if anyone wants to see an entire frame designed using any of these methods. Thanks as always to my patrons for supporting this channel and helping to make videos like this possible. And if you want to help to support me in making more content like this, there is a link to my Patreon page in the description below. Take care everybody, we'll see you on the next one.